Welcome back to another episode of the CSK8 podcast. My name is Jared O'Leary. In this week's episode, I'm unpacking the paper titled Computational Thinking for Youth in Practice, which was written by Irene Lee, Fred Martin, Jill Denner, Bob Coulter, Walter Allen, Jerry Erickson, Joyce Malin-Smith, and Linda Warner. As always, you can find a link to this paper in the show notes, which you can find in the app that you're listening to this on, or by visiting jaredoleary.com. And all of the authors that have Google Scholar profiles have a link on their name, so you can click it and you can read more papers by these authors, which I highly recommend. I've met many of these authors, and they are doing some great work in the areas of computational thinking. All right, so here's the abstract for the paper. Quote, computational thinking, CT, has been described as the use of abstraction, automation, and analysis in problem solving. We examine how these ways of thinking take shape for middle and high school youth in a set of NSF-supported programs. We discuss opportunities and challenges in both in-school and after-school context. Based on these observations, we present a Use, Modify, Create framework representing 3 phases of students' cognitive and practical activity in computational thinking. We recommend continued investment in the development of CT-rich learning environments in educators who can facilitate their use, and in research on the broader value of computational thinking. End quote. Okay, so my one-sentence summary for this is that this paper provides examples of how middle and high school youth engage in computational thinking, and it introduces the Use, Modify, Create framework, which consists of 3 stages of engagement for computational thinking. In particular, the examples draw from modeling and simulation, robotics, and game design and development. So the paper I'm unpacking today is what was referenced in the episode 2 weeks ago on the Scratch Encore curriculum. So there are 2 key questions that guide this short article. Quote, what does computational thinking for youth look like in practice? How can we support growth in computational thinking, both in and out of school? End quote. That's from page 32. So the paper begins with an intro to CT, which was a term coined by Jeanette Wing. And I've talked about this in previous episodes multiple months back. So here's a quote from page 32. Quote, thinking computationally draws on the concepts that are fundamental to computer science and involves systematically and efficiently processing information and tasks. CT involves defining, understanding, and solving problems, reasoning at multiple levels of abstraction, understanding and applying automation, and analyzing the appropriateness of the abstractions made. CT shares elements with various other types of thinking, such as algorithmic thinking, engineering thinking, design thinking, and mathematical thinking, end quote. So the authors in this paper identify abstraction, automation, and analysis as 3 key ways of using computational thinking to solve problems. Now, some of the other episodes that I've talked about computational thinking, they include some other ones, but this one just focuses on those 3. So here's a definition of each of those. Quote, abstraction is the process of generalizing from specific instances. In problem solving, abstraction may take the form of stripping down a problem to what is believed to be its bare essentials. Abstraction is also commonly defined as the capturing of common characteristics or actions into one set that can be used to represent all other instances. End quote. Here's their definition of automation. Quote, automation is a labor-saving process in which a computer is instructed to execute a set of repetitive tasks quickly and efficiently compared to the processing power of a human. In this light, computer programs are automations of abstractions. End quote. And finally, here's their definition of analysis. Quote, analysis is a reflective practice that refers to the validation of whether the abstractions made were correct. One might ask, were the right assumptions made when narrowing the problem to its bare essentials? Were important factors left out? Or is the implementation of the abstraction or automation faulty? End quote. So all of those quotes or definitions were from page 33. Also on page 33 is a helpful table that demonstrates what each of the 3 areas of CT look like in different domains, which again, you can actually find a copy of this paper by searching for it, and I include a link in the show notes. All right, so now I'm going to get into the 3 domains that they looked at. So again, these were all NSF-funded programs, so these occurred within formalized educational context or settings. So the first domain was modeling and simulation. So Project GUTS is a program for middle school students, and GUTS is an acronym for Growing Up Thinking Scientifically. The projects that middle school students tended to engage with focused on using abstraction to narrow down relevant problems and real-world problems into computer-generated simulations that they could actually then use to answer student-created problems, which I think is really cool. So here's an example that's particularly relevant to current events at the time of this recording. Quote, as part of the Project GUTS unit on epidemiology, a group of students wanted to know if a disease would spread throughout their school population given the layout of the school, the number of students, the movement of the students, the virulence of the disease, and the number of students initially infected. End quote. That's on page 33. I'm not sure if I actually pronounced virulence correctly, so feel free to hit me up if I said that wrong. So in addition to using abstraction to create models of the spread of this potential disease, they were able to automate it to simulate randomly generated scenarios, which students could then analyze to understand the potential spread of a contagion within a school population. Now, this article was written in 2011, but Project GUTS is still around, so if this particular project is still available, I honestly can't think of a more timely project to engage in at the moment of this recording, where most people are in some form of quarantine or lockdown due to COVID-19. And again, in the show notes, I link directly to Project GUTS as well as all the other projects that I'm going to talk about or platforms that I'll talk about in a moment in other domains. So speaking of, in the second domain, which was robotics, they explored the iCode program, which stands for Internet Community of Design Engineers, and is for middle and high school students engaging in, quote, a variety of microcontroller-based projects, beginning with a simple project with programmable flashing lamps, to a musical memory game, to full autonomous, self-controlled robots that enter a contest, end quote. That's from page 34. So within this domain, abstraction occurred when students designed robots that had to respond to a limited set of conditions encountered within a contest, which was a physical environment. In particular, students had to, quote, think about how to sense the world and how those stimuli will be abstracted as numerical or true-false values inside the control program, end quote. Page 34. So in other words, they might have to think about distance, which could be like how close or far something is, or true or false, like if there is nothing in front of me, move forward. Otherwise, turn to the right or something like that. So automation occurred when the robots ran the code that caused them to move autonomously. Because again, automation is essentially running the abstractions that they created, like moving straight or backing up or turning in a different direction or things like that. And then the analysis occurred when students had to determine whether the robot navigated the environment as expected and determine which conditions were not accounted for during the abstraction phase. So even though we might create a storyboard and think through all the different ways that the robot might need to navigate in the environment, once you run the automation, you might go, oh, wait, we forgot about this condition or this particular scenario. And then you have to analyze it and figure out, okay, what other abstractions do we need to change or add or things like that. Now, even though this was in the physical robotic domain, this is something that I regularly witnessed in the software side of things when kids would create their own games or apps or whatever. Now, speaking of game designs, the third domain is game design and development. So in the iGame after school program, middle school students use the program Storytelling Alice to create 3D animations for games. So students created abstractions of motion by creating methods or functions that cause a sprite to move in a particular way. Now, by the way, if you're new to the terminology, methods and functions are often interchangeable depending on what language you're talking about. So some languages refer to a function as a method, and other language refers to a method as a function, and some consider them to be two different things. And if that's too nerdy for you, don't worry about it. When the code is executed, this automates the movements of the sprites, and again, students analyze whether their abstractions worked as intended. So for example, if they're doing an animation of somebody throwing a baseball or something, so they want to have the motion of the arm moving in a realistic way, ideally, or maybe in a comical way, I don't know. Now, the authors mentioned that when analyzing an abstraction, that they often analyze for correctness and efficiency. Here's a quote that unpacks what that means. So, quote, analysis of correctness focuses on whether they produce the game they intended, i.e., whether the game plays the way they want it to, or whether the game that was designed to be fun was, in fact, fun. Analysis of efficiency involves creating the simplest code to achieve the desired behavior, end quote. Page 34. So analysis takes place throughout the overall process as testing and debugging are prevalent. However, quote, students often need an external motivator to focus on efficiency because when their game is working, they see little reason to edit the code, end quote. Page 34. Now, I too have found similar findings in the classes that I used to facilitate. If I notice that kids were working on a project, like let's say a quiz game, where if the person guessed the answer correctly, they'd get a point, or if they guessed it incorrectly, they'd lose a point, and then it'd move on to the next question, I might go up to a kid and be like, hey, that's really cool code. Want me to show you a simpler way that you can do that? And I'd show them something that allows them to kind of automate some of those processes or turn them into functions so they don't have to keep writing the same code over and over. And kids would look at that and be like, cool, that's neat, but I'm going to keep doing it my way. And honestly, it just meant that they were going to practice writing it one way. It works the same. We didn't have to worry about memory or speed or things like that in the particular platforms that they were using, so I was cool with it. However, if you want them to focus on efficiency, you might actually have to enforce it or find some kind of a fun way to make a challenge of how can we make it so that you use the least amount of code possible. For example, who can make a fun game with the least amount of code? Which, by the way, I went to MagFest, which is the music and gaming festival, in January. And one of these sessions that I went to was on creating games, art, animation, etc., using a very small amount of code. Like enough code that you could actually tweet it out in a single tweet. One of the things that I would say is that this could lead to some really interesting projects in CSK8. So, for example, like who can create the game with the least amount of code? If you are interested in learning more about that, you can go to websites like dwitter.net, DWITTER, or searching for hashtags like JS1K, which is for JavaScript 1000 in terms of memory, or searching for hashtag tinycode, and I'll include links to those in the show notes again. Maybe engaging in those resources that relate to using a small amount of code, maybe that'll give you some ideas for how you can encourage efficiency when writing code. Which again, not all kids are interested in efficiency when it comes to the code if they already have something that's working as intended. Now, at the end of this section, they do mention that there are other domains that computational thinking can be applied to. However, they only unpacked those three that I just discussed. So the next section is on supporting growth in computational thinking. So the authors encourage educators to provide rich computational environments, which are environments, quote, in which the underlying abstractions and mechanisms can be inspected, manipulated, and customized, end quote, on page 35. So an example that the authors provide is thinking about the distinction between the video game SimCity, which is a city builder simulator, and the simulator star logo TNG. Now in SimCity, the underlying game mechanics are hidden from the player. However, Star Logo allows users to, quote, look under the hood and inspect the causal relationships and abstractions that are embedded in a model, end quote. It's on page 35. In other words, in SimCity, you don't necessarily know what code is causing things to occur within the game or what kind of abstractions or functions or methods are going on behind the scenes. So for example, using Star Logo in the Contagion project that was through Project Guts that I mentioned in the first domain on modeling and simulation. So the next section is the thing that I referred to in the previous Unpacking Scholarship episode. So the authors propose a 3-stage progression that they call Use, Modify, Create, which is based on their analysis of youth engagement through increasingly scaffolded and deep interactions across these various NSF projects. So the authors suggest that the use stage is like the consumer stage where learners are playing a game or using an application. The modify stage begins to use some abstraction and automation to tinker with or modify a program or a model or a game. And the create stage is when learners begin to create their own expressions that incorporate the various aspects of computational thinking that they define as abstraction, automation, and analysis. And they suggest that learners do so within a cycle of testing, analyzing, and refining. The authors also point out the idea that the stages progress through more cognitively demanding challenges, which tend to progress along the continuum from using to modifying to creating. So this gets to some of my lingering questions or thoughts. So although the authors do mention that this 3-stage progression exists on a continuum, and that, quote, there are no clean breakpoints from using to modifying to creating, end quote, page 35. I'm curious, how much time should someone spend using, modifying, and creating before moving to another stage, and who gets to determine when a learner moves between those stages? It's not that I'm asking for a formula of you have to spend 5 minutes doing this and 20 minutes doing this, and then you can suddenly move on to the next thing. Like, that's not what I'm asking about. I'm just kind of curious, like, in general, for different kinds of engagement and for different age groups or different types of projects or languages or platforms or whatever, how much time do people tend to spend on it? And are we in fact spending a good amount of time in it in our classes? Because in general, a lot of CS educators feel pressed for time and that there's like so much that we can do, but we just don't have enough time in the day to do it. So if that's the case, are we in fact like breezing by on the use stage faster than we should and going through the modify stage faster than we should just so we can get to the create stage? And the second half of the question is who gets to determine when a learner moves between the stages? So the reason why I'm asking that, or just kind of curious about it, is because if kids are the ones determining that, what if they decide to stay on one stage for an entire year or multiple years? Or what if they decide to do it for only 5 minutes? When really they probably should have spent at least a couple of hours in one particular stage. If it's the teacher or adult facilitator or whatever that is determining this, or an assessment that's determining this, what if the kid doesn't want to move on to the next stage? What do we do then? And if we're going to have it so that the kids are kind of picking their own pace and able to move between the stages when they feel ready or comfortable, how might we facilitate a group of learners who are all spending a different amount of time in each stage? Now, this is something that I grappled with in the classroom, as I've mentioned with some of the previous interviews in particular, like with Katie Henry and with Bob Irving and with John Stapleton, where we kind of like all talk about rhizomatic learning, whether we label it that or not. When you have so many kids who are going at things at different paces and turning things like at different times, whether it be after a week or after 2 years or whatever, you kind of have to approach that very differently than if everybody's going at the same pace and are working in the same stages at the same time. And you also have to provide different kinds of support for that kind of an environment. In terms of support for independent learning or learning from peers or learning from the adult in the room, and even for the adult for learning from kids in the room. So another question that the authors kind of pose in their conclusion is that how might we assess a group of learners in this kind of a scenario, or who are engaging in this 3-stage process? And I've got some information on that I will link to, some assessment resources that I created for Boot Up, and it's free, nothing for sale or anything like that. And I'll link to that in the show notes. So if you're curious about the different kinds of assessments that I've used in the classroom, I'll include a link to that, as well as a link to an article that kind of elaborates on 3 different approaches of formative, summative, and ipsative assessments. Okay, so another like lingering question or thought that I had is what happens if we design an experience that intentionally flips or changes the ordering of the stages? So what if it goes create, use, modify? Or what if it goes create, modify, use? Or some other permutation of that? In addition, I'm also curious what stages are missing that you, as a listener or as an educator, have seen with the learners that you've worked with. So based on the article, it sounds like the 3-stage progression was developed by watching kids within a formalized learning experience or context, in particular through NSF-funded grants and projects. But I'm wondering, what stages might we uncover within informal learning environments? And how might they inform learning within formalized environments or contexts? Now, note, I asked this question with the acknowledgement that the 3-stage framework does appear to align with some of the previously Unpack scholarship episodes on mod culture, which typically occurred within leisure or informal learning spaces. In particular, the mod culture would say that modders would first begin with playing a video game, then they'd start to modify the video game by changing things, and then often they would end up creating their own video game, which follows the use, modify, create framework in this article. However, I am curious what stages might be missing if we were to look at some of these informal computer science or coding spaces. Are there things that are occurring in there that are very valuable from an educational standpoint that are missing in some of the designed formalized educational experiences? And I ask these questions not as a critique of the article or the authors or anything like that. It's just like some lingering thoughts that I had. I do highly recommend reading this article. And again, you can find it by going to the show notes at jaredoleary.com. And I also ask that you share this particular episode with somebody who might benefit from hearing about the use, modify, create approach, whether it be a fellow CS educator, an educator in a different domain, or even an administrator who just doesn't really understand this approach if you are actually using it in your classroom. I do appreciate you taking the time to listen to this. I hope everybody is staying safe and staying healthy, especially considering all the things going on in the world at the time of this recording. But stay tuned next week for another interview, and then 2 weeks from now, we will have another Unpacking Scholarship episode. Thank you so much, and I will talk to you then.